Welcome to Naradar Academy. In this video, we are going to find the solution of a second order differential equation by using the method of variation of parameters. Now let us consider this equation. A of x d square y by dx square plus b of x dy by dx plus c of x y equal to f of x. This is a second order equation, no? Because this is the highest order derivative occurring in this equation. A of x, b of x, c of x are all functions of x. They are not constants. So, we cannot find the solution of this second order equation using the method that we have already discussed in the previous videos. So, for finding the solution, suppose if we take right hand side equal to 0, if y1 and y2 are solution of this equation, then a solution of this equation can be found by using the method of variation of parameters. Okay, right? So, I have taken y1 and y2 are solutions of this equation. Then the solution of the given differential equation will take the form y equal to v1 of x y1 of x plus v2 of x into y2 of x, where this v1 and v2 are also functions of x. So after taking this as our y, find dy by dx and d square y by dx square, and let us assume the derivative v1 dash y1 plus v2 dash y2 equal to 0. So using all these things in the given equation, we can find the general solution of the given differential equation. This procedure is called method of variation of parameters. This will be clear by solving few problems. So let us consider the first problem. Solve d square y by dx square plus y equal to secant x. Now see, look at this differential equation. This is a second order differential equation with constant coefficients only. So this coefficient is 1 and y coefficient of y is also equal to 1. So constant coefficient only, this second order equation, and degree is also equal to 1. But look at the right hand side. In the right hand side we have secant x, no? So already I have uploaded one video for finding the solution of second order linear differential equation with constant coefficients. In that video, we found out the complementary function and particular integral for the specific case of right hand side. That is only for few specific functions on the right hand side we can find the solution using that method. I include the link in the description box. If you want, you go through that video. So using that method, the solution of this equation cannot be found because here the right hand side is of the form secant x. So that method is not applicable here. So let us try to find the solution by using the method of variation of parameters. So for using this variation of parameters, first we should take the right hand side equal to 0, so that this equation will become d square y by dx square plus y equal to 0. Let us find the complementary function of this equation. So for finding the complementary function, we have to write the auxiliary equation. It is m square plus 1 equal to 0. So m square equal to minus 1. So m equal to plus or minus I. So the roots are complex conjugates with real part alpha equal to 0 and imaginary part beta equal to 1. If the roots are complex conjugates, the complementary function is e power alpha x into a cos beta x plus b sin beta x equal to e power 0x into a cos x plus b sin x. E power 0 is 1. So a cos x plus b sin x. So here look at this cos x and sin x. This cos x is our y1 and sin x is our y2. So this y1 is a solution of this homogeneous equation and y2 is also another solution of this equation. Okay, and they are linearly independent. Okay, so now what we are going to do is, by assuming this as y1 and this as y2, we are going to find the particular integral by using the method of variation of parameters. So the general solution will take the form y equal to v1 y1 plus v2 y2, where v1 and v2 are not constants, they are also functions of x. So from this y, let us find what is dy by dx. So y is equal to v1, what is y1? Cos x, and y2 is sin x. So v1 cos x plus v2 sin x. Let us differentiate this. See, since v1 and v2 are not constants, they are also functions of x, no? So while differentiating this term, you have to use product rule for differentiation. Okay, v1 into differentiation of cos x is minus sin x plus cos x into v1 dash, plus for this term v2 into differentiation of sin x is cos x plus sin x into v2 dash. Okay, so here we have to assume the terms containing derivatives of v1 and v2 equal to 0. So this is the condition that we have to assume in the method of variation of parameters. that is v1 dash cos x plus v2 dash sin x is equal to 0. So after taking this is equal to 0, dy by dx will be only minus v1 sin x plus v2 cos x. Now differentiate this again and find d square y by dx square. This is equal to minus v1 dash. Again product rule I am applying here. So sin x keep it as it is, minus v1 dash into sin x. Next minus v1 into differentiation of sin x is minus cos x plus cos x into v2 dash plus v2 into differentiation of cos x is minus sin x. So I find what are the values of y, dy by dx and d square y by dx square. Now I am going to substitute all these values in the given differential equation. What is the given differential equation? D square y by dx square plus y equal to secant x. So substitute the values. So minus v1 dash sin x minus v1 cos x plus v2 dash cos x minus v2 sin x. Okay, plus y. Y is equal to what? v1 cos x plus v2 sin x equal to secant x. Okay, this minus v1 cos x and plus v1 cos x get cancelled. Minus v2 sin x plus v2 sin x get cancelled. So finally we get v1 dash sin x plus v2 dash cos x equal to secant x. Take this as equation number 2. Equation 1 is, while finding the first derivative, we have assumed the terms containing derivatives of v1 and v2 as 0. No, that is equation number 1. Now I am going to solve these two equations, equation 1 and 2, and find the values of v1 and v2. Look at these two equations. Here it is v1 dash sin x. Here it is v1 dash cos x. So multiply this equation by sin x and this equation by cos x. Okay. So 1 into sin x implies v1 dash sin x cos x plus v2 dash sin square x is equal to 0. Second equation into cos x implies minus v1 dash sin x cos x plus v2 dash cos square x is equal to cos x into secant x. These two terms get cancelled. So here we have v2 dash into sin square x plus cos square x is equal to, here cos x into secant x. Secant x is nothing but 1 by cos x. So this value is equal to 1 only. So v2 dash into, this is 1, no, sin square theta plus cos square theta is always equal to 1. So v2 dash equal to 1. So v2 equal to integration of 1 dx. So integration of 1 is what? X. X plus integrating constant c1. So we find the value of v2. Next, for finding the value of v1, let's substitute v2 dash equal to 1 in equation 1. In equation 1, substitute what? v2 dash equal to 1. So it will be what? v1 dash cos x plus sin x equal to 0. So v1 dash equal to minus sin x by cos x. Let's integrate this. v1 equal to integral minus sin x by cos x dx. See, if you differentiate the denominator, differentiation of cos x is equal to sin x, no? So if you have integrals like this, the answer is log of the denominator. So that is differentiation of cos x is minus sin x. It is there in the numerator. So the value of this integral is equal to log of the denominator cos x plus integrating constant c2. So v1 equal to log of cos x plus c2 and v2 equal to x plus c1. So substitute in the value of y. Y is equal to what? v1 cos x plus v2 sin x, no? You substitute the values and expand. So y equal to log cos x into cos x plus c2 cos x plus x sin x plus c1 sin x. That's all. So this is the solution of the given differential equation. Let's see one more problem. Solve x minus 1 d square y by dx square minus x dy by dx plus y equal to x minus 1 the whole square, given x and e power x are two linearly independent solution without the right hand member. See, this is a second order differential equation and the coefficients are not constants. Okay. This is x minus 1, this is x minus 1 the whole square. Okay. So the coefficients are not constant. This cannot be solved by second order linear differential equation with variable coefficient. In that way also we cannot solve. Okay. So we are going to solve this by using the method of variation of parameters. What is given here is without the right hand side. If this right hand side is 0, x and e power x are solutions for this equation. So no need to find the complementary function. We can only find directly the particular integral. Let us take y1 equal to x and y2 equal to e power x. Okay. Then y equal to v1 y1 plus v2 y2. That is v1x plus v2 e power x. Now differentiate this. What we get? v1 into 1. Because here this is product, no? v1 and v2 are not functions, are not constants. They are also functions of x. So v1 into 1 plus x into v1 dash plus v2 into differentiation of e power x is e power x plus e power x into v2 dash. So what is our assumption? The terms containing the derivatives are equal to 0. So xv1 dash plus e power x v2 dash equal to 0. So what is dy by dx? v1 plus v2 e power x. Again differentiate this. D square y by dx square is equal to v1 dash plus here product rule. v2 dash into e power x plus e power x into v2. Okay, now substitute all these values in the given differential equation. So x minus 1 into v1 dash plus v2 dash e power x plus v2 e power x minus x into v1 plus v2 e power x plus v1x plus v2 e power x is equal to x minus 1 the whole square. Okay, now let us expand and cancel the terms. So finally we are getting the equation like this: x minus 1 v1 dash plus e power x into x v2 dash minus v2 dash is equal to x minus 1 the whole square. That is x minus 1 v1 dash plus x minus 1 e power x v2 dash equal to x minus 1 the whole square. So v1 dash plus e power x v2 dash equal to x minus 1. So this is equation number 2. Now I am going to take both equation 1 and 2 and subtract them. This is equation 1 and this is equation 2. So if you subtract, these two terms get cancelled. So x minus 1 into v1 dash equal to minus x minus 1. I am subtracting these two equations. Okay. So v1 dash equal to minus 1. So integrating we get v1 equal to minus x plus c1. Put v1 dash equal to minus 1 in equation number 2. So what you get? Minus 1 plus e power x v2 dash equal to x minus 1. So v2 dash equal to x e power minus x. So we have to integrate this by udv method. U equal to x and dv equal to e power minus x dx. du equal to dx and v equal to minus e power minus x. So integral udv equal to uv minus integral v du. Okay. So minus x e power minus x plus integral e power minus x dx. So this is minus e power minus x plus integrating constant c2. So what's the solution? v1x plus v2 e power x. So substitute the values and simplify. So what you get? Y equal to minus x square plus c1x minus x minus 1 plus c2 e power x. So this is the general solution of the given equation. Okay, that's all.